So anyway, so this is our first live Zoom colloquium. So the past two virtual colloquium have just been canned. But today, Dr. John Walkup, Roger Key, and Stephan Squire are going to talk about some of the work they've been doing in regard to introductory physics labs, which is really exciting, really cool. And so without further ado, John.
All right. Okay, so I have a rod here of 6 feet length, and I'm going to poke Doug with it if he gets in within striking distance, as I call it. So I'll go ahead and kind of introduce the actual topic here, and then we'll turn it over to others. What we have been working on for the past couple of years now is sort of reinventing the labs to meet, I think, career-ready realities that our students are going to be facing. And we want to also make it more engaging and where they learn more practical skills. So where does this all come about? What's the impetus for all this? Well, I think that Stephan can kind of tell you, and Stephan has worked at the TA level and is working at the high school level. He's a high school teacher now. So Stephan, why don't you tell us a little bit about your experiences with the learning the skills attainment by our students and yours?
Okay, so traditionally in the traditional physics labs, it's kind of very cookie cutter, or it's recipe where students are following directions and they don't have very developed skills in critical thinking or statistical analysis. So basically, as you can see, some of the statistics, it's kind of alarming that students that are not prepared for this kind of fall out of this STEM. This is even true for high school students, as they typically are very used to kind of like chemistry-like things where they say, take this and then do this. So we're trying to get them out of that in order to get them to critically think and create their own types of labs in order to implement them. Right. And in hopes that it's going to improve the enrollment and the statement in STEM class or majors.
Right. And, you look at these statistics, and the question I have at the bottom, of course, is do these reflect Fresno State? And I think most of us would look at that and probably say, yeah, we suffer from, and our students suffer from much of the same. These statistics were compiled at the University of Cincinnati, but I think you can go into almost any university.
John,
and similar things.
Just a moment. I'd like you to know that we have a couple of people joining the colloquium who don't have cameras or may not be watching the video. They're on the phone line.
Oh, okay. Then I'll just be as descriptive as I can. Luckily, this meeting doesn't, or the presentation doesn't rely on any real figures or anything like that. So they should be fine. Okay, everybody. All right, so what are some of the major, changes that we made in our approach? One of the things that we looked at was having a more industrial strength statistical analysis package for these labs. When I came back to the university, I looked at the statistics that we were doing and thought these were just not appropriate for preparing students for engineering careers and physics careers. We were doing a lot of percent errors, percent differences, when reality is, things like p-tests and p-values and standard errors and standard deviations. That's really the language of science. The other one major difference that we have is what we typically do as TAs. We get in together and we set up the experiments ahead of time, and we work hard to make the experiment as good as we can, and then we turn the experiments loose on the students. So students never really learn how to actually design a lab. Everything is designed for them. And in these experiments that we created, much of what they learn is how to actually design labs to uncover meaning. We replace the verification of content, which is typically the traditional way that labs are set up. If you're going to learn that momentum is conserved, then you go into the lab and you have an experiment laid out for you where you compare the momentum before and after, and you verify what you learned in the lecture. That is done almost everywhere, but it has significant problems with it, and we'll talk about that in a little bit. Our results, when students get done in the past, they always got an answer like 4, and they compared that with what they should have got, which was maybe 4.2. And success was determined by how close their results matched what was expected. But that's not very real world. In the real world, you don't know the true answer. If you did, you wouldn't have to do the experiment. And so we replaced this verification of content with estimation. So students tell us what they estimate, for example, what G is equal to, and then they only find out how well they did or how close they got after they have submitted their report. So they have to talk in terms of confidence in their results rather than how close they got. One of the things that came out, and I think that Jack, I think, mentioned this, he was in my lab, the heightened algebraic manipulation. In other words, if you're going to do experiments and you're trying to uncover an estimated value or something, you have to express that unknown in terms only of known properties, measurable properties, things you can directly measure, which requires that you do a lot more algebra than you do in most of your homework activities. Furthermore, to reduce the error in your results, you have to have the minimum number of mathematical operations, something that you learn in computational physics. And therefore, you have to simplify your equations down as much as you can. For the first time, students now are seeing, oh, this is the reason why we have to simplify our equations, right? Yeah, there's a reason why. Too many mathematical operations introduces too much rounding. We also brought in LaTeX as a skill development in that, because I thought that learning LaTeX would be really good for future engineers and scientists to learn. And then we also cast our activities in terms of these learning objectives, and they are put into tables. And the reason why we do that is to make sure that as they pass through 12 activities, that they are uncovering a broad range of skills and concepts and not focusing on one and pounding it over and over again. So for example, in the communication, in this particular lab, which is the barbarian lab, students are going to learn how to write figure captions. That is the writing part of this lab. And they're also going to learn how to insert captions into LaTeX. And then under reinforced, there's a lot of these concepts and skills that they go over again and reinforce over time. Okay, let's see here. And so, Stephan, why don't you talk a little bit about your experiment that you ran here for your master's thesis?
Okay, so my master's thesis was basically a study of Fresno State's. It was our second, I guess, rollout of the new Physics 4A lab manuals, at which we were using, or we were working in collaboration with the University of Cincinnati, and they developed a test to basically measure scientific reasoning called the I-STAR exam. So what we did was we gave 2 sections of the lab, the traditional lab, and 2 sections of the new lab manual. And we gave them the test prior to the class, and then we did it at the end of the class to see how, if there was any increase of their scientific or scientific reasoning and statistical analysis, if there was an increase of their skills in those aspects. And what we found is that there was a positive relationship between the new Physics 4A lab manual versus the old one. However, our study size was too small to basically be of significance. So basically what that told us is we have to continue the study and continue forward and seeing if there was a direct correlation between it.
Yeah, we had 3 measures there. One was the I-STAR critical thinking exam. We also looked at the force concept inventory.
Yeah.
And then we also had our own
The finals.
oh yeah, I'm sorry, yeah, the final exam,
Okay.
which common final exam against all of the students. And these new activities we created have generated so far 4 publications in referee journals, and I have another one on the way, and Jimmy Gonzalez and I are preparing another one as well. We'll talk about that a little bit later. Yeah, Doug.
So actually, I'm here live. Can I ask a question?
Sure.
So this was for a lab class. So you gave them an actual exam in the lab class?
No, it was the final exam in their lectures.
Okay.
Right. And it was really kind of ideal because that way it was the lecturers administering the actual assessment, not people involved in the study. It was also really helpful. You know, we really bent over backwards to eliminate confirmation bias as much as we could. One of the lab activities represents a CURES program, and that is now in the CURESnet database. And a tighter adherence to the ISO and NIST definitions for statistical analysis. A lot more career focus, so we talk a lot more about what engineers do and physicists. And real explicit instruction in writing, so students are taught how to write a discussion section rather than just assuming that they've learned this prior and asking them to write a full lab report. Okay. Roger, what about the reduced equipment demands? Do you have any comments on that?
Well, I must say that we're fortunate to have plenty of equipment, but the reduction in the need for those, well, there's other concerns, I would say. Making sure everything goes back where it belongs when you're done, and things like that. But no, I think it would be valuable to give the students training on how to use the more sophisticated equipment, and then cut them loose on it when the time comes.
Right. And the nice thing about this approach is that because we want error so that we can examine, analyze it, we're not stressed out in trying to get the high dollar equipment to reduce error. So it's a completely different approach to this. Let's see here. Oh, by the way, yeah, we established a collaboration with University of Cincinnati and got paid for it, which is really nice. So that was really neat. And now I want to talk about some of the labs that we actually developed. There are 4 of them that I want to focus on, and I'll show you the rest of them. Time in a light pulse. Hey, Roger, why don't you tell us about the first time that we grappled with this idea?
Well, John, you know, the first time you brought that to me, I thought you were nuts. What are you going to do sitting in front of a clock with a stopwatch? Aren't they both measuring the same thing? And then I realized that this is a way to introduce statistical analysis to the students that is really simple, really easy to understand, and gets them going in a way that nobody else ever did.
Yeah, what we developed was the process of experimentation. And this lines very tightly with the NGSS standards. And the idea is that if you want to measure an unknown pulse duration, and I was using pulsars as sort of a test for this thing here. So in a pulsar, you see a new pulsar, you got to measure its time, its duration. And how do you go about doing that? Well, it's a process. And the first thing that you do is you got to find a method of timing that produces low variation. In other words, you want a process that produces minimal standard deviation, irrespective of how close it is to the true value. And so students would go through, find out which of the students is better at timing, by better meaning lowest variation, which between a stopwatch and a iPhone, which one of those produces the most consistent results. And then they examine their results with terms of the standard deviation, noticing that this is all about reducing random error. At that point, once they settle on the optimal method, they then go to another known 5-second duration. I'm sorry, not another, but they go to a known 5-second duration from a clock, and they measure the bias by finding out what their mean measurement is and how far it is from the 5 seconds. And then they can calibrate their results for the bias. Only then do they turn on the unknown pulse duration from the Arduino device. Let me show you here. So what I have in this slide is step 1, where they lower the precision. And then step 2, they calibrate against a known clock duration. And then in step 3, they estimate the unknown time. After they turn in their lab report, that's when they find out what the true time is supposed to be. And I have here at the bottom to express their estimate in terms of confidence intervals using the standard error. I did that the first time, and I decided after that to make that more later in this. Actually, it was in the next lab activity rather than this one. I tried to kind of chunk this thing along so they're only incorporating statistical measures one at a time. This is an interesting experiment we developed centered on industrial manufacturing. In this case, it was clay ball bearings. This was published in the American Journal of Physics. Oh, by the way, the previous one was published in Physics Education Journal. This was in the American Journal of Physics. And Patrick Talbot was on this, and also my son, who helped us during the summer. In this case here, students manufacture clay ball bearings. So the whole idea is that they roll balls of clay, and they have to roll these bearings within a certain target mass. And there's tolerances associated with that. So they can't make the bearings too large or too small. And this is designed to mimic Six Sigma, which is a industrial strength quality control system that's pretty much dominates engineering now and business. This is also their first foray into data-driven decision making. So they use data to make choices on how to improve the system. To do that, they employ what we call the PDCA, continuous improvement cycle. This is an actual formal hands-on activity designed to teach that continuous improvement process. As far as I know, this is one of the very few activities ever done that. This teaches inferential statistics. So you only sample a certain number, and from that small sample, you have to infer what the population exhibits. And more than anything else, I don't think I've ever seen an experiment that delineates between random and systematic error so well as this one does. The journaling process, students have to keep tight journals on all the decisions they make. That becomes a part of the lesson, which is also kind of a nice deal. So the PDCA cycle, if you'll notice the target mass there, this is data actually from one of our research groups, team groups, student groups, and their target was 10.8, and those red dashed lines are the tolerances. They cannot, or any bearing that they make that's above 11.9 or below 9.7 is considered a defect. With a 1.5 sigma process, we can't do 6 sigma. I mean, that's impossible with what we're doing. I chose 1.5 sigma because it's reasonable. With 50 bearings that they make, they can't have more than 7 defects. So the first thing they do is they brainstorm a way to actually make these things. They manufacture 6 bearings, and then they run the statistics on it. Most importantly, the standard error and the mean. And then, based on what they see, they decide to alter their manufacturing method for improvement. They're required to choose either random or a systematic error to improve. And they go back through it again. They build 6 more. They do the statistical analysis. They choose a new method. Unless the old method was better, then they revert back to the old method. And they do this cycle until, well, actually, we only have them do 3 rounds because that's all that we can really do in the time frame. But normally, you would continue to do that cycle until you're satisfied with your output. And I would say in the engineering world, they would probably still continue doing it. So in the end, this is what it's all about, a real sharp contrast between the sample statistics and the population statistics. And here you can see what happens to the standard error. If the standard error is too large, it can shift your population over to one side or another too much, and you end up with too many defects. But notice also that if your mean is too far off, which means high systematic error, that also produces a lot of defects. So this lab activity really strengthens students' understanding of the standard deviation, standard error, confidence intervals, and such. And then catastrophic, I call this slide catastrophic collisions, but what this really is that, well, okay, here's where this starts. I was doing the elastic collision lab, and in the elastic collision lab we had, we would have one of the targets sitting motionless and the other one would hit it. And I thought, you know, that's kind of limiting. I said, no, I mean, the only way you're going to learn how to conserve momentum and energy is to have the objects moving against each other, because then the sign plus or minus on the vectors and momentum become important. So I had my students do it, didn't even think about it. And they came back with 100% error, 200% error. I was thinking like, what happened? And then after a while I realized, oh shoot, when you conserve momentum by comparing the momentum before to momentum after, you're subtracting numbers that are very close together. And so the amount of error in comparison to the size of the measurement skyrockets. Now I taught computational physics at Cal Poly, where this, which we call subtractive cancellation, was really important to eliminate it. That dawned on me. So we'll go to the next slide. This is a schematic of the actual collision, and you'll notice that if we compare the momentum before with the momentum after, you get horrible results. This is signified by the thumbs down. If you, however, compare the gain in momentum of one car versus the loss of momentum in the other car, you get very good results. Why? Because comparing the changes means you're adding these momenta. You don't have to subtract the cancellation problem. And then it dawned on me that the same thing applies to energy. It's just the opposite, because energy is a scalar. So if you try to compare the total energy before the collision with the total energy after, you'll get terrible results. However, if you compare the total energy before the total energy after, you get very good results. And then if you compare the change in the energies, you get terrible. For the same reason. So I thought, what a great way to teach students about this problem with catastrophic, with this elastic collision lab and the problem with subtractive cancellation. An issue that shows up in computational physics all the time, but is not talked about much outside of that. So we created an activity. We got it published in Physics Education, and so it's in the literature now. And then we have the SpeedyLucis game. I know that you do a lot more SpeedyLucis than I do, Roger. Do you want to talk about this one?
Well, I have to say, actually, I don't use your method. I use a slightly altered method.
What? That's okay.
I find keeping score to be tedious.
Yeah, why don't you talk about what Elucis expresses, the way you do it?
Well, what I do is I write a card on the whiteboard, and I say, okay, there's a pattern established here. In the pattern you're looking at now on the screen, you see the ace of clubs, the 3 of clubs, the 5 of spades, the 7 of spades, the 9 of clubs, and then a question mark. So what could be the next card? Well, you might infer from the series shown that if you're only shown the first 2 cards, you might think it's increasing by 2 in clubs only. But then that 3rd card changes your mind because it's 5 of spades. So now you might think that it's increasing by 2 black cards only. However, you get to the end there and you see the question mark. So after 9, you have ace, 3, 5, 7, 9, and then what? So whatever card shows up there, if it fits the pattern established by what we're calling nature, maybe it's the Jack of Diamonds, and it fits. So then you have to change your hypothesis or your theory, whatever you want to call it, to include just simply increasing by 2. Originally, if you only see the first 2 cards, you think it's increasing by 2 clubs. If you see the first 4 cards, you think it's increasing by 2 black cards only. And if you go on out to the question mark, and if the Jack of Diamonds fits, then you would say, okay, it's simply increasing by 2. And the way I do this in my class, usually the first lab, is by doing much a similar thing on the board. However, I think it's valuable to show them the cards that don't work. So my class is typically in 9 groups, and I allow each group to work together to decide on their next card. And they tell me a card, and if it fits, I move it to the right. I write it down on the board to the right. And if it doesn't fit, I write it down on the board below. Because I think it's valuable for the students to see what didn't work.
Right.
Okay.
Mm-hmm.
And in this version, you know, keeping score is a bit tedious, so I don't keep score. I just go around the room once, and if they all get it right, we're done.
Right, right.
But they can still publish. They can still retract. They can still, well, what's the other one? Replicate.
Replicate.
Right.
So Elusus Express is a pretty old game, and it's been used to teach the scientific process for many, many, many years. It kind of dissipated after a while. I hadn't seen it being used. I was taught this game at the University of Oklahoma by one of the professors there, and thought it was really neat. It teaches a lot of scientific vocabulary. So playing this game, because you see it's a pattern guessing game, you have to formulate a hypothesis of what you think the pattern is. Then you play your card, which is like performing an experiment. Nature rejects it or accepts it, depending on whether it matches the pattern, is a confirmation of your hypothesis. And once you develop this model for the pattern, if all of the groups have agreed that it's the model, then that becomes a law. So the game is designed to teach scientific vocabulary and the whole inductive process. Notice falsifiability is really important here. So if you see a card that shows up that doesn't match your pattern, then your pattern was wrong. Your model was incorrect, so it's been falsified. It also is a perfectly good example of inductive reasoning. And what I did was changed it up to speed the game up, but most importantly, developed this idea of publication, replication, and retraction. And the idea is that if you think you know the pattern, and this is the speed loose I'm talking about, if you think you know the pattern, you declare publish, and you tell everybody what you think the pattern is. Now, this is where it differs from traditional Elusus like Roger teaches. Then, if other groups think they agree, they can replicate your model. At some point, though, you might think that you've got the wrong model, in which case you can retract your publication. And there are point values that are assigned to all these things designed to make the game competitive. But Roger's right. I think it's just as fun to play without all the scorekeeping. This game is also an advantage of complete, and I say it can be played online. Actually, Roger and I are starting to work the kinks out of that, and we're having some issues there. So I'll put a question mark on that first one. This is a great icebreaker. If you're looking for something to do during your first time you're with lab, and remember, that first week, students are filtering in and out. You don't know who's going to stay the next week or not. A lot of times, labs, they just don't even meet. But you could play this game, and students can learn a lot of vocabulary and learn a lot about the scientific publication process and make that hour or 2 hours worthwhile. It's faster paced than Ulysses Express. And look at all the questions you can generate from this thing. How does this game model Occam's razor? That's a good question. Students can investigate that. Is competition healthy in science? You know, this is a competition. Are there any downsides? Students can investigate that. You look at falsifiability and inductivism. Cold fusion. They could go back, they were born well after this, but they could go back and look at cold fusion and see what happened there and see if Speedy Lucis has something to say about that. And then, of course, we have our famous frauds in science disasters that have occurred over the years, and Speedy Lucis. It's interesting for students to examine that in light of the card game. So we do have a little bit of time here, so I'm just going to roll through the other labs that we have developed. Those with an asterisk are primarily designed by Kathleen Koenig from the University of Cincinnati, who we collaborated with. One is the density of clay. So we get these clay bricks, and the students sample parts of the brick. They measure the density of these samples, and they have to decide whether the brick is of uniform density. This is a quality control issue. If you're going to be involved in creating clay for a project, measuring the variation in the density of the clay is an important measurement. So, and for this one, they have to use error propagation. And the reason is they're taking measurements of the mass and all three sides of the brick. And the only way to express the standard deviation of the brick itself, you have to use error propagation. So this is their first time that they have to do error propagation in a classroom. The pendulum experiments, they're designed to identify what are factors and what are non-factors. Okay, like for example, the mass on the end is a non-factor. It's the factor in the experiment is the length of the pendulum.
John?
Yeah.
I think it's worth mentioning here that it is also an investigation of what is the difference between independent and dependent variables.
Oh yeah, you know what? I'm glad you brought it up, Roger, because that's kind of the major point, right? Is to determine the difference between an independent and dependent variable. And then pendulum experiment 2, they do a little bit better measurements. They try to find a functional dependence on the length of the string. Projectile motion is different. Our old projectile motion experiments, they only estimate the range at which the ball hits the ground. And Kathleen looked at that and said, you know, what's better is if they make the thing go through a ring in the midpoint of the flight. So in this, guys, they find the range where it hits the ground to find the initial velocity, and then they use that initial velocity to position the ring so that the ball goes through the ring. And this is a well-liked lab activity. Students like it. Even though students initially, when they look at it, they think, there's no way in the world I'm going to get the ball to go through that little tiny ring. Over half of the class usually gets to go through. We have some really excellent slow-mo of some of those. Notice that they have to also They have to calculate the orientation. So they have to know the direction of travel. So they have to do that arctangent thing on the velocity vector to do this. Whereas our older lab, they didn't have to do that. So this lab is much more rigorous than the previous projectile motion lab. Newton's laws, this is the hanging mass on the cart deal that we do traditionally. Here they have to estimate the mass of an unknown object. They are not told the mass until after they turn in their lab reports. And this is designed to show the difference between interpolation and extrapolation. And the next one, they do the same exact equipment to calibrate the system to eliminate the friction, which is a source of bias in the experiment. Let's see what else is kind of interesting here.
John, may I interrupt for a moment?
Sure, go ahead.
I don't know if you're watching the chat, but Joseph says he's got video of the projectile experiment, I think it was.
All right.
He says the lab with the ring was awesome. And Jack says it's all
like
a
it.
lot of fun.
Yeah. Is there a way to show it when we get done?
Yeah, it's in the chat, so
okay.
It'll be recorded as well.
Okay, well, I'll click on the link when we get done with the rest of them.
Very good. Thank you.
Yeah. And let's see what else. Oh, the interesting one here also is the rotational motion. In the past, if you remember, we had this disk, and we were to find, I think we were trying to estimate the moment of inertia of the disk by physically measuring it and using 1/2 mr squared, and then also timing it as it angular accelerates from a hanging mass. And that was fine. But I thought, you know what would be better? Let's take a couple of half disks, half circles, semicircles, made out of steel. Let's stick this on the platter. Now the students, to find the moment of inertia, they have to use calculus. So it forces, and they have to use the parallel axis theorem. So they have to use both of those things to find the moment of inertia to compare to. And so it was my attempt to inject some calculus into our lab activities. And then some future work that we're doing. Jimmy Gonzalez and I are working on a lab manual comparison. He's leading this research, and he collected about 20 lab manuals from around the country. Some of them community colleges, some of them 4 years, some of them elite. And we're finding out that there's vast inconsistencies and in many cases simply incorrectness in the treatment of, mostly is what we're mostly interested in, is error and statistics. And we're finding that there's just little agreement amongst lab designers on what these things all mean. Some of the stuff is just simply wrong. But we're going to do the comparison, and Jimmy's going to submit this to Physics Today as a paper. Very eye-opening what we see there. And it does show the need for physics departments in general to tighten down their statistical lecture to NIST and ISO standards. I mean, most governing bodies have have established protocols and definitions, and we really need to tighten those down. We also are working on a CURE project involving essentially hypothesis testing. We're going to do both t-tests and p-values, and we're going to use the elastic collision experiment for that. The elastic collision experiment is nice because momentum, if you have eliminated error, momentum before is the same as momentum after, and the energy before is the same as the energy after. And what we're going to find out, I'll guarantee you, that we're going to confirm, well, I should say, we're going to reject the hypothesis that momentum is conserved using one of the approaches, mainly measuring the change of the momentum, And we're going to fail to reject the hypothesis if we use the momentum before, we can momentum after. And I just got that one backwards. What I said is 180 degrees backwards, but you get the idea that using the same experimental data and mathematics, that's perfectly appropriate. You can confirm, I should be careful, you can reject a hypothesis or fail to reject the hypothesis in the same experiment. And the whole idea behind I should say the motivation behind this is to show that you can't take p-values too seriously. You always have to take everything with a grain of salt, and that's the whole idea behind that. Guided inquiry is a form of instruction for teaching students, and the 5E method is the most common way. So we've decided to modify one of our existing lab activities to go full bore guided inquiry. Rather than just playing lip service to it. It's very easy to say that you have a guided inquiry lab, and it's not really guided inquiry. So this is going to enforce guided inquiry protocols. I know that Roger and I have talked a lot about having one of our experiments be a reading comprehension experiment instead of writing. We haven't ironed out exactly what that's going to look like yet. But we think reading comprehension is a major problem with a lot of our students. And so why not develop some activities where reading comprehension sort of takes precedence over the writing skills, at least momentarily. I'm working on a radiation safety experiment with the bond class I'm teaching. The revocator that you see in the picture there, I have one of my own. It's not nearly as pretty, but it's highly radioactive. And I just ordered a radon detector, which has arrived today. We also have the survey meter. And so students are going to be doing experiments by telling me what they want to do. So they order me around and I do the measurements for them, and then they do the analysis. So we think that we can get a publication out of this. I think this is a really cool experiment. And there's like 3 or 4 different things that we decided we could do. Testing the radon in the water, testing the radon the outside, inside the revocator, looking at shielding effects, things like that. Yeah.
So I can't see what's on the screen, but maybe for the students, I think maybe everyone knows what a revocator is.
Oh yeah.
Maybe.
Yeah, it's a crock pot that's lined with radium. And
Tell them why they were lined with radium.
What's that?
Tell them why.
Well, the idea was that you would put the water in it at night, get it nice and radioactive, and then drink the water in the morning. And there's 2 problems with the revocator. One, it's got radium-226, which is alpha generator. So drinking the water introduces alpha into your internal organs. And while alpha has no penetrating power, it has major destructive power on the thin layers it does encounter, and therefore it can create all kinds of cancerous tumors. And the other problem with the revocator is the daughter product of radium-226 is radon-222, which is the 2nd leading cause of lung cancer in the country. And so this thing chugs radon-222 out constantly. And so we're doing some experiments on that. And one of the things that they used to do was they would put a cover over the top of one of these crock pots and then inhale the gas from it. They knew that the gas created by the revocator was radioactive. They didn't know what it was. Radon had not been discovered yet. But they figured, hey, if it's radioactive, it's got to be good for you. So basically they were inhaling radon-222. I can't imagine how long they lived doing that.
John?
Yeah.
I got a comment about that. Some years ago, a student named Mario Badal, I don't know if you remember him.
I don't think
was
so.
Worried about my health.
Doug does.
Yeah, Doug remembers him. He was concerned about me breathing radon in my office because this darn thing was stored in my office. So he took a radon detector and he put it inside the cabinet with that device. Left it there for a week. And I have to say, there was no radon detected.
Really? Interesting. Okay, that might, now by the way,
Maybe the detector was on a lower shelf and the device was on a higher shelf, something like that.
and you want to know why you probably didn't detect any?
Go ahead.
Radon is about 10 times heavier than air.
Well, it probably just sank and
It
vanished.
sank in the bottom of the revogator, and that's what we're going to investigate.
Okay, cool.
Is the radiation levels as a function of depth. So I'm kind of surprised that none of the radon made it over the edge. That's what we were going to investigate, but not terribly surprising. It simply means that the radon emanates slow enough to where it doesn't build up fast enough to creep. Do you remember how long you left the thing sitting there?
Yes, he left it for a week.
Okay. Be interesting to see if over a longer period of time, if any of the radon starts to creep over the top of the.
Well, that's possible. I still have the detector.
Mhm.
We could do it again.
Sure. By the way, we stored it in your office because none of us wanted to volunteer for it. We all said, you know what? Yeah, it's stored over here in room 174 now. Momentarily until we get done.
Well, yours is, but I have two.
Oh, you have two more
I
Revigators?
have another one besides yours, yes.
Is it Zender's?
Yeah.
Oh, okay, Mike Zender's. I didn't know he had it here. I thought he had it at home. This is nicer. Much nicer. So, by the way, on the final point here, I am overhauling the lab manual, and it's got some really cool features. First of all, it's being done all in LaTeX, which we have been working on, Roger and I have been working on for a long time now. The statistics is much tighter and much more sophisticated than we've had in the past. There's also a modular TA version, so I can turn off and on the TA version of the manual. So TAs get all of the explanations, like, you know, the answers to questions, tips on what to say to students if they have a problem, and things like that. We also have a bank of standardized quizzes in there that TAs can choose from. And the whole idea behind that was so that our quizzes from one lab to another are, you know, somewhat uniform. And these quizzes are put into categories like physics concepts, experimental techniques, statistical properties. So TAs are, you know, they're kind of encouraged to kind of pick a broad range of things to ask. And the TA version has the answers to all the quiz questions. The TA version would be available online, and then we probably would sell the student ones in the library, or not the library, but the store. So that was the whole idea behind that, and I think it's going to work out really well. So I'll tell you what, I have not had the chat on. I don't think I can see the chat from when I'm sharing my screen. I've tried it before, but I got nowhere. So I'm going to go ahead and stop the share here and dive into the chat to see if anybody's got any comments and stuff like that.
Hey, John.
Yeah.
The chat has been somewhat active. We've got comments from Avery, Jack, and Joseph. And
I forgot to mention that Avery and another student named Sean Mount were involved in and published part of some of the experiments that we did.
that's excellent. Yeah. Okay, so if we have a few minutes left, I think I'd like to make some comments.
Sure.
Okay. Pardon me. So I asked earlier of all the TAs teaching 2A, 2B, 4A, 4B for comments about how the virtual labs are going. And I got a couple of different responses. One is so far so good. This particular TA set up a whiteboard in his room and is able to describe things on the whiteboard to the students live. And then another TA gives us comments about the students are not getting as much out of the labs as they were face-to-face. They are struggling to connect the concepts in the labs, the virtual labs, with the lecture. That could be because the virtual labs are not tailored for our lecture courses, but most have expressed a clear preference for the in-class labs. Pardon me. So from the teaching perspective, it's difficult to check for understanding because the TAs do not have a direct connection with the students. Normally they're walking around the room, checking on the tables, looking at what they're doing, and that's not happening now. So this TA's response is the labs can be done entirely online is a resounding no. We might need to keep some emergency online lab program that is tailored to our lab, our lecture courses, because she mentioned earlier that, that the disconnect between the students' understanding of the lab and the lecture is because we're doing this on an emergency basis. And then another TA comments, so far so good. I got a whiteboard. I put it behind my desk.
I would suggest, Doug, that purchasing some smaller personal whiteboards and having them ready would be probably a good idea. Because if I had one that was like maybe this big, I could probably go home and do it.
John?
Just an actual whiteboard?
Yeah.
We already have about 48 of those.
Really, where are they?
They're down in the hallway between my office and 162.
I mean, I've been down here risking infection all this time, hanging around Doug, which is might as well just shoot me at this point.
No, what you should do is go down the ramp in my office and turn left after you go through the door all the way to the end. You'll find a bunch of whiteboards and markers.
Oh, okay. Oh, I have a few comments from the chat room here. Joseph mentions that when he did his ball bearings, all of them were too small, and it was because of confirmation bias. Jack, what happened? You can turn on your microphone if you want.
I think what happened. Can you hear me?
Yeah.
All right. So what happened is I was kind of cutting corners on the process, but then one of my other teammates was also kind of cutting corners. So like I think instead of following the PDCA cycle, I was like kind of going off with what I thought needed to be changed without really documenting it. And then my other team member was doing that too. And then those two added up to where every single ball bearing we made was smaller than what it should have been. So we just did a poor documentation, and we weren't communicating as a team.
You know what also happens a lot is students will be like, for example, when they're timing the pendulum, right? And they're timing it and they're shutting off and they're looking at the time they got and then recording it. But when you do that, you can allow your previous measurement to affect your next measurement. So if your times are coming out shorter than you think, you might be leaving the timer on longer than you just to compensate. And that's a source of confirmation bias. So my students know that they turn off the timer and they show it to their lab partner. They don't look at the time on their deal. It's all about eliminating confirmation bias. And it's again, it's going back to Richard Feynman said that, the whole part about intellectual integrity is bending over backwards to make your results as meaningful as you can. And that's how you do it. Let's see, there was some other interesting.
Actually, one thing that we tried in our lab group was the person who was timing wouldn't look at the timer, but they would be allowed to like say, "Oh, that one didn't feel right," and we would be forced to like delete that off our list, even if it felt good to us. So I think that really helped too, because it gets rid of those ones where, let's say, you misclicked or something happened without adding in that confirmation bias.
Yeah, and in the past, what students would do is they would look at the number and say, "Oh, that's what I must have made a mistake," right? But here, they don't look at their response. They make the decision whether it was a good time or not and reject it. But as soon as you look at the time, now you're making your rejections based on what you think the time should have been, and that's a source of error. So yeah, there's a lot that goes into these labs. Avery mentioned, he was really quite astounded that with the collision lab, you can have the same data manipulated with perfectly good mathematics and come up with completely different results. And it's all because of the error inherent in the actual mathematical operations themselves. See here, Roger, you want to go ahead and play the ring, the ball going through the ring? Did he post that?
No, I don't have that yet.
Oh, okay. Well, here it is.
Oh, it's in email?
It's at the very bottom. No, it's in the chat room. It's a YouTube.
Okay, all right.
Yeah, I just uploaded mine.
Okay, I can share it then. Hang on
Okay,
one.
why don't you do it.
Yeah, I'll do it. Hang on. Just give me 1 second here. Just slow loading, but we're getting there. It's taking a while.
Hey guys. I have to take off. I have to be somewhere around 4:15.
Okay. Hey, thanks for joining in, Stefan, and your contributions.
Oh, no problem. You guys have a great day. Thank you for inviting me.
Okay, here we go. It's just now, it looks like it's going to get started here. Okay, so I'm going to go ahead and share the screen again. Okay, so here it is. There is the little target that they have to make the ball go through. It's pretty small. I appreciate Dave for taking the time out to make these targets for us. The students look at that and they say, there's just no way. But this is the result of, and keep in mind, they have to place the target and then they have to orient the angle of it so that the ball goes through perpendicular to decrease the chances of it hitting the side. And let me see if here it goes, right through. Everybody see that? I'll do it one more time. Right through the middle. I think it's cool. Okay. Okay, Joseph, we got it through. You okay? Okay. Let's see here. Let me go through the chat here and see if there's any other comments. And it was choppy for Roger. So maybe it was a little bit on the choppy side for people. And so, sorry, I don't know if I can fix that problem. I think it's just, I noticed that the YouTube took a long time to load, and I think that's the problem. I think it was just the signal was low. All right, guys, it is the top of the hour, and if we don't have any other questions or comments, we can go ahead and end the session. If you have any questions or comments, now's the time to punch them in. Okay, well, it looks like we're finished up for the time.
Hey, John?
Yeah.
I got one other comment from a TA about the virtual labs.
Oh, okay.
So he says they are harder to teach, but they're easier to grade.
By the way, everybody should know that the virtual labs he's talking about are not the labs we did in this presentation.
Okay,
in fact,
so that brings up an extension to this discussion. How do we take what we're doing here and make it virtual?
Yeah, we have talked about that, and you know, that's going to be an ongoing discussion, and maybe others that are attending this can forward some ideas of their own. But with the virus thing and everybody having to do everything remotely, that raises a problem for labs. Now, we talked about having students doing the pendulum lab on their own, which they can do. All it takes is just a rock hung on a string and a timer, which is on their phone. So there are some things that we can do, but probably a little late in the semester for doing that one. So yeah, we're going to have to think of some ideas here to make the lab more engaging and learning as much as they did in the past. Tough chore. Go ahead.
As a theorist, of course, I know the answer. But actually, what is it? So let me just say, like, if all the people on the chat or on the Zoom, if they know, like, this is what you teach me in your class, we can discuss later. But if they don't know, I mean,
John, I can't hear him.
Yeah, that's okay. I'll rephrase it. He wanted me to kind of just go over quickly what a t-test and the p-value thing is. In the past, if we had two different ways of measuring something and we wanted to compare those measurements, we would do a percent difference, right? That's real low level it's kind of bad. So what you do is not only do you compare how far the means are from each other, but you divide it by how much overlap there is in the standard error. And that's the t-test. And think of it as a signal to noise ratio. So the signal is how far the means are from each other, and the noise is how much overlap there is in the uncertainty. And
there's a lot of overlap, a lot of noise.
Right. So the idea behind the t-test is there enough signal noise ratio to confirm that these are distinct values? So there's two ways of doing that. One is if the two means are very far apart. And the other one is they could be very close together, but there can't be any noise or very little noise. Exactly. So the t-test is a ratio, a signal to noise ratio for making those comparisons. Much, much closer to what you would do in the real industrial world. P-values, well, that's a lot more. I'm still working on the p-value lab now, but what was that?
You said something sort of offhand or backhand about p-values.
Well, what the problem is that he's asking about what is my issue with p-values. The problem with p-values is it's this statistic that people generate, and they look to see if it's less than a certain value. And if it's less than a certain value, they all throw their hands up in congratulations, and they say, we have demonstrated, or sometimes they say proven, which is really a problem, right? And it's all based on this value, this magic property. The trouble is what this lab is designed to show is that, and by the way, the p-value is used to determine whether to reject or not reject a hypothesis, okay? The problem, what we're going to show in this lab is that with the same exact experimental data and using only mathematical operations that are well-defined, you can reject the hypothesis or fail to reject the hypothesis in the same experiment. So it shows that the p-value, you really have to look at it. You just can't take it for gospel. There's reasons why you could have a very low p-value and still have garbage. You know, and a lot has been written on that. But I don't know anybody that has ever devised an experiment to purposely illustrate how a p-value can confirm a notion and reject a notion at the same time. Yeah, you know. No, we haven't done the experiments yet. I'm pretty much about 90% certain that the results will come out like I think they will, and that we will be able to reject a hypothesis and not reject it by the same. So
is that confirmation bias right there?
Well, no. I mean, you want your results to be irrespective of that, right? So you work hard to eliminate the confirmation bias. No, the actual dilemma, or let's say the inconsistency, is caused by the subtractive cancellation in the data. So
Agreed.
one way of comparing momentum versus another way of comparing momentum, one results are going to be really good, the other one's going to be really bad, but it's the same data. So it should be an eye-opening research deal. Avery, me, and my son are working on that now. And I think Sean, who's an engineering student, will also be joining in. But we'll see. But with the virus coming along, we sort of had to kind of sidestep that for the time being. Avery, do you have any comments on that you know of, or are you good?
I think I'm good.
All right. Hey, thanks for signing in.
Of course.
Roger, I don't have much of anything else. Oh, by the way, I should mention, Avery and Sean were in my Physics 4A lab when we did the experiments. That's the reason why it was a Cure project. And they got really interested in this. So after the semester was over, we met during the summer and kind of tightened up things, and that's where we produced the paper.
So if you make another paper out of the replicator, this is the second.
Well, we already have one paper that's a Cure project. Well, if this one also, the p-value one, that would be 3 Cure projects. Not bad. Not bad. I don't know if you heard what Doug was talking about, but he was talking about the number of Cure projects that we can generate over the last year or so. And if everything comes together like we think it will, it'll be 3 of them. Published papers and the CureNet database.
Mm-hmm. I am not familiar with the CureNet database. I'll have to look into that.
Well, you're familiar with Cure.
Oh, yeah.
Yeah. Well, it's just when you get done, you have to upload your experiment and you have to fill out certain protocols and forms and stuff. It's pretty tight. You know, there's a certain format and everything that you have to adhere to. It takes a while. You know, it's a long process to get it loaded up, but I finally got the one we already did with the catastrophic cancellation paper up there. So others can now download it and implement that experiment in their own universities. Because the Cure thing is kind of like in a community of its own. And so they, create and share experiments.
Absolutely. Yeah, the virtual labs are much the same way. There's all kinds of databases online for that. And I think I would, if anybody's interested, let me see who's left. No, I don't think anybody's interested. Okay. So I have a Google sheet, a spreadsheet with a lot of virtual lab resources.
Right.
If you want it, email me. I'll send it to you.
Roger, I think we're good to go now.
Okay.
So thanks, everybody. I appreciate you coming. Oh, wait, Doug's got something to say.
Yeah, so we're going to take John's.
Hey, so thanks, John. Thanks. And if anyone's on campus or near campus and you're of age, so 21 or over, we're going to take John out to have a beer, and that means my wife just brought me a 6-pack of beer. I'm going to sit in McLean 162. I'm just kidding.
Just kidding.
Okay. All right, anyway, so have a good weekend. Have a good spring break, everyone. And yeah, if you're around campus, like in the next, say, 10 or 15 minutes, just come by the physics office or McLean 162.
All right, take it easy, everybody.
Is Roger frozen?
No, he just doesn't
He
move.
just moved? Wow.
No, I think he actually is frozen. Wow.
Oh,
Oh, there he
okay.
goes. All right, take care.